Hello and welcome to Lecture 5 of the Forces unit of Phys 1101, and this whole lecture is going to be about one of the most crucial skills you'll develop in this course, which is drawing free body diagrams. So we need to start by talking about what a free body diagram shows, but actually maybe first it's more relevant to ask why should we even bother to draw free body diagrams? Well, I think obviously the answer is we do it because mean physics professors make us. No. Free body diagrams are to help organize your thoughts. You spend your time thinking about a physics problem, about an object that you're trying to figure something out about, while you draw your free body diagram. So that by the time you're finished drawing the free body diagram, you're usually most of the way through solving the problem, even though you haven't written an equation down yet. And in the end, the free body diagram is all about writing down an equation, because what we then do, which we'll do not in this lecture, but in the next unit, is we translate the diagram directly into a statement of Newton's second law, right? An equation. The sum of the forces over the mass equals the acceleration. And so what the free body diagram is all about is showing the forces. You show all the forces that are acting on the object, and then you show the net force. I'm going to start by working an example, and then I'll summarize the process with a list. So let's think about this. A crate is being lifted up vertically by a crane, and the crane is speeding up at some rate, and a bunch of details are given about the crate. They're not important for us here. And what we want is the tension in the cable that it's being lifted by. So you should really start by drawing a pictorial representation of the situation, okay? And the thing is that we're really only interested in the crate. So it might be tempting to, draw the crane and so on, and the cable and the crate. But no, that's not what we want. All we care about is the crate. So just draw the crate. And in particular, it's being lifted up. It's not on the ground, but it's attached to a cable. And that's that. That's everything. So now remember, I advocate that you now draw a circle around it. Now, eventually you'll be practiced enough at this that this step won't be particularly necessary. And what this circle is showing us is that the only thing attached to the crate is the cable. And so the only contact force will be a tension. And then, as usual, we'll have the long-range force of gravity, the weight of the crate. Okay, we've now identified all of the forces that should be acting on this crate. And now it's time to draw the free body diagram. So you now draw some representation of the crate. Now, in this course, you'll always just draw it as a point. And remember, this is because we don't care about rotations or anything like that. And so we can always get away with thinking about objects using the particle model. In a more advanced course, you might draw the crate still as a box. Okay, and I'll do it this time, but I'll never do it again in this course because we want to do this, because this leads to distractions. So now you just put all the forces on. You draw them as vectors pointing out of the object. So I'll do it on both of my diagrams here. So that's the weight, and I'll label it in a moment. And here's the tension, and I'll label it in a moment. So it is important to label all of the force vectors so that you can tell what's what on your diagram. So there we go. And the next step is to put the net force vector on. Now you don't put it on the diagram itself. The diagram should just have all of the forces that act on the object. The net force is the sum of all those forces. So it isn't a force on the object, it's the sum of all of the other forces. So, which way is it? This crate is speeding up as it goes up. So it's accelerating in the direction it's moving because it's speeding up. And so Fnet must point up. So there's Fnet, and I'll put it on the other diagram as well. There. There's one last step. We should draw a set of axes somewhere. Now, some people like to put it on the object. Some people like to put it beside. I kind of prefer putting it beside because I find it gets in the way of all these other arrows we've already drawn. But some people like to put it right on the diagram because they find it helps them figure out how to take components of things later on. So that's your own preference, whether you add it on top of your diagram or beside it, right? So I've just added it beside. If you put it on your diagram, it would look like that. Okay, but I'm going to put mine out here. One more note about your axes. If you look in many textbooks, they'll advocate that you draw your axes before you draw your forces. I don't think that's a good idea, because a lot of the time you want to strategize about whether you want to tip your axes or something like that. And the time to do that strategizing is after you have all your forces on the diagram, because that you use the forces on the diagram to decide how to orient your axes. So let's summarize what we just did. You start by identifying all the forces acting on the object, and you should really do this before you even start drawing your free body diagram. Next, you draw a representation of the object, and throughout this course that'll just be a point because we're using the particle model. Then you draw vectors representing all of the forces. So every force you identified goes on to the free body diagram. You draw them out of the object and you label each force. And although it hasn't come up yet, it's important to label them uniquely. So for example, if there are two normal forces acting on the object, don't call them both N. Do something like putting a subscript on them so that you can tell them apart. Then you draw and label the net force vector, and you don't attach it to the diagram because it is not a force on the object. It's the sum of all the forces on the object. So you put it somewhere beside the diagram. And if you think the net force is 0, then you write that down instead of drawing the net force vector. And finally, you draw a set of axes on the diagram or beside it, whatever your preference is. Let's do another one. This one's a little more complicated. So we have a child riding a sled down a hill, and some details are given that don't matter to us at the moment. And what we're going to do for the moment is just draw a free body diagram of the sled. So I'm going to say, start with a pictorial representation. So here's the hill, and here's the sled. And here's the child. And as usual, I'm going to draw that little circle around the sled. That's the thing we're trying to draw the free body diagram of. And I note that it's touching the surface of the hill, the snow, whatever that is. And it's also touching the child. And so there are going to be contact forces due to both the surface and the child. And that should be everything this sled is touching. So that means the child, that's a surface-on-surface contact, so there will be a normal, and there could be a friction. And again, this is a surface-to-surface contact, so there will be a normal and a friction. And given that it is sliding down the hill, you can guess there will be a friction. We'll talk a lot more of friction in the next unit. For now, I'll just say this is going to be a kinetic friction because the sled is sliding on the snow, whereas presumably the child isn't in the process of falling off the sled. So the child is not sliding on the sled, not slipping, and so this would be a static friction. So let's now draw the free body diagram. So I'm going to go straight to just drawing it as a point. And I've identified all the forces. And now note, I've got 2 normals and 2 frictions. Now the frictions I'm going to use different symbols for, even if I'm not careful about that, because I think one's a static and one's a kinetic. But these 2 normal forces, I'd better be careful to use different symbols for them. So let me start with the hill. The normal force due to the hill is going to point this way. And so I'm going to call it N sub h for hill. Okay, and then this friction force, the sled is going down the hill. That kinetic friction should oppose that motion, and so it should point up the hill. Okay, so far I've got N sub h, a normal due to the hill, and F sub k. Then the normal force due to the child. Well, the child is on top of the sled, and again, the normal force will be perpendicular to that surface of contact, so that means the normal due to the child is going to point down this way. And so that is the normal due to the child, N sub c. And then there's this tough question of which way the friction force due to the child acts. And that's a toughie. I'll say it actually depends on a bunch of things, and I'm not going to worry about it overall right now. It is somewhat likely that the friction on the child would point up the hill, and that would mean that the friction force on the sled would rather counterintuitively point down the hill. But don't worry about that right now. We'll talk about that a lot more in the next unit. All I'm trying to do is get all the forces on here. And then the one other thing that we must not forget is our long-range force, the weight. And so the weight of the sled points down. Now, many students would want to say, oh, and the weight of the child. No, no, no. The weight of the child is a force exerted by the Earth that acts on the child. It does not act on the sled. It acts on the child. And so it doesn't go on this free body diagram. If we were now to draw a free body diagram for the child, that force would be on that free body diagram. The way the child pushes down on the sled is this normal force. So the one remaining thing to do is draw the net force, and I haven't told you whether this sled is speeding up or slowing down. And so it would be a guess. So I'm going to guess this sled is speeding up and put the net force pointing down the slope. And so the last step is to draw axes. If this is going down the slope, it makes sense perhaps to put our x-axis positive down the slope. And we'll talk more in the next unit about strategizing about when you should tip your axes and when you shouldn't. But if you just look at this, almost all the vectors are tipped. And so if we put our axes tipped, we're only going to have to break the weight into components. All of these others point along an axis, whereas if I left them upright, we'd be breaking all of these into components, then the weight would be the only one we didn't. So it makes less work here to tip the axes.